To do a little bit of beam deflection practice. So the two equations you need to know for this are the inertia equation, so I equals base times the height cubed divided by 12, and the beam deflection equation is delta max equals the force times the length cubed divided by 48 times the elasticity times the inertia. So going through reading this, there's a lot of information in these couple of sentences. First, we know that the carpenter has a weight of 187 pounds. That pounds tells me this is going to be a force. Then I know I'm walking across a joist. The joist tells me how that piece of wood is set up. So a joist goes up and down kind of like this. So up and down, and then it goes back the length of the joist. These first two numbers in the name of the joist, 1.5 by 3.5, those two things tell me about the cross section of the beam. So if I'm looking at this, because it's a joist, it's taller than it is wider, so I'm going to say the smaller number, 1.5, is the base. And the 3.5, the bigger number, is for the taller line, 3.5 here. This last one, 12 feet, tells me how long or how far back that beam goes. But this is in feet, these are in inches, so I need to do a conversion. Since there are 12 inches in 1 foot, I'm going to multiply 12 times 12 to get a length of 144 inches. So this beam goes back 144 inches, that's my length. I know that this beam is made out of wood and it has a PSI of 9 million. So this PSI, anytime you see PSI, that's going to be your E, your elasticity. And I think that's it for finding our variables, so during the construction of the house. Good. So now we're going to use these two equations that we wrote down. So we're finding the E first. So the B stands for the base. The base is always going to be the horizontal number from your picture. So my base is 1.5 times the height, right? So that's the other end, the height, 3.5. And I'm only cubing the height, and then divide by 12. So if I put that into my calculator, if I did order of operations first, I do 3.5 cubed equals times 1.5 equals divide by 12, and I get my I value 5.36. Then I'm going to take this information and plug it into the delta max. So delta max equals the force, which I get from up here, force, 187, times the length, we've got here, right, the length back of the beam, 144, that gets cubed, divided by 48, which is a constant. E, I get up here in my equation, so 9 million, times I, which I just calculated in the step above, so 5.36. So again, the order of operations is super important. I'm going to do the exponent first. I'm going to do 144 cubed equals times what's next to it in my numerator, 187, equals. Then I'm going to divide by everything in my denominator. And since I want to group that all together, I'm going to put it in parentheses. So I'm going to do parentheses 48 times 9 million times 5.36 gives me my beam deflection of 0.24 inches. Okay, so that's how we're going to solve a beam deflection for a joist. We're going to do one more example. Since this beam was a joist, we're going to do one that's a plank. So using the same two equations as above, the inertia equals the base height cubed divided by 12, and the beam deflection is delta max equals the force times the length cubed divided by 48 times the elasticity times the inertia. So going through and getting our variables. So a gymnast who has a weight of 115 pounds, that's my force, pounds is force, is performing a beam routine on a plank. So planks are set up where they are wider than they are taller. So my plank is going to look like that. Has a dimension of 2 by 4 by 16 feet long. So again, these first two numbers tell me about the cross section here. And since this is wide and wider than it is taller, I know the bigger of the two numbers, the 4 inches, is going to go here on the bottom and the 2 is going to go on the side. Now this 16 and a half feet, gives me the length, but this is in feet. I need it to be in inches. So I'm going to take 16.5 feet and multiply by 12 since there are 12 inches in a foot, and I get my length of 198 inches. The beam is made of Douglas fir wood, so that gives me my PSI, my elasticity, my E is always represented in the PSI. So we're going to use all of this information to find the beam deflection. First, we're going to find the inertia by using the inertia equation. The base of this is 4, so I'm going to do I equals 4 times the height, which is 2, only the height is cubed, divided by 12. Doing our order of operations exponents first, so I'm going to do 2 cubed equals times 4 equals divided by 12 equals my inertia of 2.67. Now to find my beam deflection using the delta max, I'm going to do delta max equals my force comes from the problem. Up here we labeled the F115 times the length, we converted into inches, 198 cubed, only the length, divided by 48 times the elasticity in the PSI, so that's 13 million, times the inertia, which we just calculated, 2.67. And again, order of operations, super important. Exponents first, we're going to do 198 cubed equals times everything else in my numerator, 115, equals divided by my entire denominator, which I grouped together with parentheses. So parentheses 48 times 13 million times 2.67 gives me my beam deflection of 0.54 inches. Okay, so now we've got an example of a beam and a joist. Joist and a plank. Joist and a plank. Remember, joists are up and down, planks are side to side. So the orientation matters because it affects your inertia. And you get those information from the first two numbers in the information about the beam. Okay?